Video 4, this is omega B97X-D. You'll notice that B3-LIP was pretty long, and the acronyms for the middle two were kind of short. Now this one is like piling it on. Quantum chemistry is really quite remarkable for generating lots of acronyms, but this is the last we're going to deal with. So omega B97XD. Let's see if we're going to pack it. There's going to be a hybrid there because it's got exchange. There's going to be an explicit inclusion of dispersion, that is long-range interactions, and it's actually going to be done empirically, and it's like an add-on to the functional. Becca 97, so we're not using Becca 88 anymore. And this W, which really should be an omega, tells us that what we're going to do is we are going to switch over distance between how much GGA exchange we use and how much exact exchange we use. That is, in all the other functions we looked at, the exchange is an even weighting no matter where you are in the distance from the nucleus. But what you're going to find here is that the exchange near the nucleus tends to be mostly GGA. And at large distances, it's almost all exchange, and that fixes up the behavior of the orbital at large distances. And the omega, which should be here, is a tuning parameter. It basically decides where you switch over. Now, you can look up the paper. I don't have it here, but that's what we can do. So here's the philosophy. We're going to retain the LD behavior as it goes to uniform electron gas. That's a target. There's a new expansion form for the enhancement factor that is actually power series in the reduced gradient, excuse me, S. There's no explicit inclusion of second derivatives of rho, so it is not a meta GGA in the same way that M06 was. But it's long range corrected. Here's what I was talking about the omega. It switches with distance from local to fully non-local, and it improves the shape of the energy density. The -D adds an empirical dispersion correction to get weak interactions right, and that's important in organic molecules where, you know, you may be making a bond here, but what bounces into each other over here can have a big effect. And one of the things they emphasized here is a controlled incremental fitting procedure. So they build up the fit as they add data and stop when there are no enhancements of the results. So here's the paper. And this is pretty close to the state of the art today. It's from 2008. There may be some functionals that are improved, but this is an impressive functional. And so I'm just going to show you some results and give you a sense of, you know, where it works and where it doesn't. So this is a summary of performance of various functionals for the atomization energies in a large test set. And this is just telling you whether it's long range corrected. It's telling you whether it goes to uniform electron gas. But let's just see the numbers. These are the mean absolute errors. And what you see is B3-LIP, our old friend, is at about 5 kcals per mole for this test set. You see that omega B97X, this is not XD, but X, is at about 2. And then you could find M05-2X, which is comparable as the M06-2X, and it sits down here. So, you know, they're all pretty impressive, but it is the case that, at least in this comparison, omega B97X does better on average. Okay, so it's going to be hard because the next table that I show you should have this heading as well. So just remember, the first column is the reference energy, like the best calculation we know how to do to give us an estimate of a barrier height. Oh, I should say, these are heavy atom transfer reactions. So here you got H coming up to N2O and pulling off an oxygen. Here you have H coming up to HF and pulling off a fluorine, and so on down here. And I'll only focus on a couple. So here's the reference barrier height. Here's omega B97X. That's pretty good. Here it is without exchange. And that doesn't make sense. I'm not sure I know what omega B97 non-X is. I'm sorry. B3 lip, considerably worse. B lip, considerably worse. And that's one of the things we know is that for barrier heights, B3 lip is not terribly accurate. Let's look at the chlorine exchange. Here's 18, 20, 12, 9. So, that's pretty good compared to the high accuracy calculations. All right, remember these. First one's delta E ref, omega B97X. Here's B3 lip next to last. Because these are nucleophilic substitution reactions. So I'm going to take an F and displace an F minus, displace an F minus, and you can do all sorts of, which is the first one. Here you see that the barrier here is pretty tiny. And you get a number similar to that here. And you get larger numbers for B3 lip and B lip. So here's another set of atomization energies. So how do these functionals do? Here's the mean absolute error, 3.6, and omega B97 beats out everybody. That doesn't mean it is always the best. You can see its maximum error on the plus side is larger than B3 lips, although B3 lip may have gotten luckier in those. Is maximum error on the negative side is smaller than everything else. So it gives you a sense that there's this, steady is probably the wrong word, but episodic approach to a better functional, that adding pieces that are important, like turning on exact exchange at large distances, but maybe not at short distances, can help. The dispersion can help. And so there you are. So this was a summary of functionals, a summary of survey of functionals. None is perfect. That's the first thing I want to say. Each has different components and each has different philosophies. Approaching solid that's not solids, what I really want to say is pretty impressive accuracy. But there are still problems for systems that are diradicals or complex transition metal bonding. Things that we would have to describe with more than one resonance structure. The questions I think awaiting us are, can we get a lot better? Will machine learning help with this? I tend to be skeptical, but I was online with a friend of mine yesterday who convinced me that there might be hope. Can we do it without training? I don't think so. I don't think it's possible. That is, if you were to go back to the PBE philosophy, it sort of runs out of gas at about an average, a mean absolute error of about 8 kcals. I think we'll always have to train. Can we break bonds smoothly? There are people working on that, but the methods are pretty cumbersome. We can do it better than Archie Fock, but not at present. So that's what I got for you. And I'm going to let you think about what this